So this is the Helisalter. It's our project by Caden Parody
And Henry Nelson and Michael Marchev.
and Fayu. The natural model we wanted to base this off of was the helicopter leaves called Samaras from trees. They usually spin when they fall out of the trees, causing dispersion of the seed pods, which allows the trees to spread out their saplings. Our design goals was to kind of base it off of this toy here that gets slingshotted up, and once it's up there, it gets caught by the wind and spirals as it comes down.
These are the materials we decided to use for our first prototype. We found all these for free at Phylac or EXP. And this is what it looks like. It's just a center dowel with these two paper wings coming off from the side and a cuboid like storage mechanism in the side. And this is a description, a drawing of what we were going for. So it was good on auto rotation, which means it started spinning as soon as it fell. It was also very lightweight, which was ideal, but it had kind of poor structural supports, likely due to the weak materials that we used, and it had a bad payload storage mechanism. So our improvement plan was to incorporate hinged wings, which is part of our original plan, and use better materials and to lower the center of mass.
The second prototype, we used all these materials here, most notably the 3D printed hinge mechanism that held the wings in the dowel. Um, as you can see from these videos, it ended up falling and breaking out of the drag. Um, this was mainly due to the heavyweight 3D printed hinge compared to the rest of the materials that had a high center of mass, which caused it to instantly flip over. So there's no auto rotation, weak wing material because it exploded, and it wasn't able to hold a payload. For the next project, we wanted to make the bigger wings with better materials and have it be able to have a payload in order to lower the center of mass.
All right. So our third prototype was mainly 3D printed, but you can see we use chopsticks here as hinges in between this connector part and this T part. So the wing was slotted into the connector, and the connector was slotted into the T with the chopstick as a hinge. So this worked well with the chopsticks. It was able to pivot quite nicely. The payload was placed well, as you can see here. This is the payload. This piece is able to slide up where you can put in salt. Um, but the problem is the wings never opened up. We had the same problem as last time where it was just too heavy in the front and not heavy enough in the payload. So we need to add more weight to the payload to make it so that it orients itself correctly and the wings open up. So what we need to do is make lighter, low-density wings, smaller hinge mechanism, and sturdy materials because it broke upon impact and we don't want that to happen again.
So we incorporated all these in the fourth prototype, and these are the materials we used. We bought laser cut wood to cut the wings, and we also had kosher salt as a payload. We also bought crazy glue. And this is what our fourth prototype looked like. It incorporated these smaller hinged mechanism, a more round storage capability, and this is the full wingspan. It's huge, and it was very lightweight wings. This is what it looked like when we were recording it. This is with no rotation needed. And you see it just glides down. This is with some rotation into it. And you see that it does maintain a rotation when it gets glide down. So after that, our wing broke off because it was not yet. What happened was there was no auto rotation, and so it kind of nosedived and broke apart. But we did like that this material was lightweight, and we liked the big surface area we had. We liked that it was able to withstand so many strong impacts at first. We liked the look of it, and we also liked that the wings opened when falling most of the time. We didn't like, or we did like the low center of mass, but we wanted to change the wing angle, which could hopefully help with auto rotation. We also wanted to mend the broken wing.
Great. So finally, this is us mending the broken wing. You can see we're using various materials, mainly super glue here. As you can see, we're holding this part in where it's snapped right above the payload. And over here, it's snapped at the wing. You can see us taping things together here. And finally, we use duct tape. And there we are printing the new hinges, which are shown here with a 10-degree angle on both wings, causing them to put force such that it rotates. Here we have the wing design with a bar in the middle to allow for higher stability and higher strength. These wings took many, many impacts and never broke except at this critical point right here, where we would definitely beef up in the future. Um, Here you can see a test flights.
Hi, Brett. Spin it. Spin it. I'm not going to spin it. It should spin on its own. Okay.
And you can see it does spin on its own. It does spin on its own. And towards the end, it comes forward a little bit. See right there, it came forward, which indicates that if you were allowed to keep flying from a higher distance or launch it higher, it would continue forward and achieve the goal of delivering a payload over a large forward area. So what we achieved was that the wings were very lightweight with a large surface area to mass ratio. We used very sturdy materials and was able to withstand multiple strong impacts, except at some critical, very weak points, which we would beef up in the future. It was visually appealing, which might be useful if you want to use this as a teaching, prop to children. It could even be used as a toy. And the wings opened while falling, which allowed the other things that we incorporated to take and catch the air and cause the rotation and slow it and move it forward. We had a low center of mass, which again caused it to flip the correct way and the wings opened. And like we've said the whole time, the goal is auto rotation, which we achieved. Unfortunately, it was the weak orange wing, again, due to that critical point which you need to beef up. So if we were in the future to improve this, continue with this project, we would definitely want to re-laser cut the wings and test with a higher launch zone to allow it to move forward into more space. Additionally, we might want to angle the wings upward a little more as they are in the actual Samara, but that would be a change in the T part where you're connecting both of the connectors to the wings.
Some other applications that we could use is for agriculture, distributing fertilizer or seeds to help with the farmers, fire suppressants, so to disperse things to put out forest fires. We could use it in the military to deliver goods to soldiers without using any electronics, or a fun glitter bomb for a party. Thank you.